In this video, we will take a look at the so-called logarithmic differentiation formula, which tells us that the derivative of a function f is equal to this function itself multiplied by the derivative of the natural logarithm of this function f of x. This formula can be very useful because sometimes it's much easier to compute this derivative on the right-hand side, so the derivative of the natural logarithm of our function f, than to compute the derivative of this function directly. Now, the only thing we have to be careful about is that we can only plug in positive numbers inside the natural logarithm. So this formula can only be used when the function f of x is positive. Now, to see where this formula is coming from, let's take a look at this derivative on the right-hand side. So the derivative of the natural logarithm of f of x. So here we plug in one function f of x inside another function natural logarithm. So it means that we can use the chain rule, and the chain rule tells us that this will be equal to the derivative of the natural logarithm, which is 1 divided by whatever is inside, in this case f of x, multiplied by the derivative of the inside, so f prime of x. And then if you just multiply both sides by this denominator f of x, you see that you get exactly this logarithmic differentiation formula. So this formula might look intimidating at first, but as you can see, it's just an application of the chain rule together with the derivative of the natural logarithm. Now, let's take a look at one application of this formula, and let's compute the derivative of the power function x to the n when n is arbitrary real number. Now, of course, you probably already know this formula, but if you try to compute this derivative just by the definition, it's not going to be so easy when the power n is not an integer. So instead, let's see how we can use this logarithmic differentiation formula. Okay, so it tells us that we should take our function x to the n and multiply it by the derivative of the natural logarithm of this function. And then the reason why this is easier is because here we can use the properties of natural logarithm. In particular, we can take this power n outside of the natural logarithm. So we can rewrite this as x to the power n times n times the natural logarithm of x prime. And now we just need to compute the derivative of natural logarithm, which we already know is just 1 over x. So this will be equal to x to the n times n divided by x. And then if you cancel x, you get exactly what you want, n times x to the power n minus 1. And as you can see, in this calculation, it didn't really matter if this power n is integer or not.